In the natural world, movement is not just a way to travel. It is strategy. It is survival shaped by millions of years of evolution. And among all forms of movement, there is one that feels almost like a break in reality itself: the jump. A sudden explosion of force, a moment where the ground is left behind, a brief defiance of gravity. For most animals, jumping is simple: a way to escape danger, a way to catch prey, a way to move faster than walking allows. But for a few extraordinary creatures on Earth, jumping is not just movement. It is engineering. Biological engineering so refined that it turns living tissue into a living machine of energy release. And in some cases, it becomes so extreme that distance compared to body size defies intuition. Tonight, we enter that world, the world of Earth's most extreme jumpers. To understand these animals, we must first understand what a jump truly is. A jump is not just muscle strength. It is not just leg power. It is energy storage, timing, structure, and physics working in perfect synchronization. A biological system that loads energy and releases it in a fraction of a second.
And in some species, this system has evolved into something almost mechanical: a living spring, a biological catapult. We begin with something almost invisible, a creature so small it can easily be overlooked. It lives in soil, grass, and hidden damp environments all over the world. It does not fly, it does not run fast, but when threatened, it disappears instantly. This creature is the flea. At first glance, a flea seems insignificant, only a few millimeters long. A simple insect living quietly among mammals and birds. But its jumping ability is one of the most extreme in the entire animal kingdom. A flea can jump up to 200 times its body length. If a human could do the same, we would leap over skyscrapers in a single motion. This ability is not powered by raw muscle alone. Inside the flea's body lies a remarkable biological material called resilin. Resilin is an elastic protein that behaves like a super efficient natural spring. Before jumping, the flea slowly compresses this system. It stores energy gradually, like loading a mechanical trap. And then, in a fraction of a millisecond, it releases everything at once. The result is not just a jump. It is a launch, a biological projectile fired into the air. But fleas are only the beginning. In fields and forests, another jumper demonstrates a different kind of power. More visible, more familiar, but still incredibly efficient. The grasshopper. Grasshoppers are masters of explosive movement. Their hind legs are not just limbs. They are energy storage systems built for precision release. Before jumping, a grasshopper locks its legs into a bent position. Muscles tighten. Energy builds up slowly. And then, suddenly, the lock releases. The result is instantaneous. The legs snap open faster than the human eye can track. The grasshopper launches into the air with accelerations exceeding 20 times the force of gravity. For a brief moment, it is no longer grounded. It becomes airborne through pure biological force. No wings required. No external propulsion. Only stored energy released in perfect timing. But evolution did not stop there. In damp environments and forest floors, another small jumper exists. Less known, but equally impressive: the flea beetle. Flea beetles earn their name from their behavior. When disturbed, they jump suddenly and unpredictably. Their hind legs are enlarged, like pistons. They function as biological springs that store and release energy in rapid bursts. To predators, they seem to vanish instantly.
One moment they exist, the next, they are gone. But now we move even deeper into the microscopic world, where jumping becomes even more extreme in proportion to body size. This is where we find springtails. Springtails are among the smallest jumping animals on Earth. They live in soil, sand, leaf litter, and hidden damp environments. They are often unnoticed, but their jumping mechanism is one of the most unique in nature. Instead of relying only on legs, springtails use a specialized structure called a furcula, a forked appendage tucked beneath the body. When released, it snaps against the ground with incredible speed, and the springtail is thrown into the air almost instantly. The acceleration is extreme for its size.
Not just fast, violent in biological terms. A survival mechanism designed for instant escape in a world where danger is constant and reaction time is everything. And this reveals a deeper truth. The smaller the animal, the more extreme its jumping ratio tends to be. This is not coincidence. It is physics. At small scales, muscle power alone is not enough. So evolution builds elastic storage systems instead. Biological springs, energy amplifiers. Now we move to larger animals, where jumping becomes less about escaping microdangers and more about agility, speed, and survival in open environments. In the savannas of Africa lives one of the most iconic jumpers, the impala. The impala is not the strongest animal. It is not the largest, but it is one of the most agile mammals in the wild. It can leap up to 10 meters in a single bound and reach heights of around 3 meters. But what makes the impala remarkable is not just distance. It is control. Impala can change direction mid-air. They can land and immediately jump again, without hesitation. Their movement is fluid, unpredictable, and highly adaptive. For predators, this makes them extremely difficult to capture, because their trajectory is never fully predictable. In the ocean, another jumper exists, one that uses water instead of land: the dolphin. Dolphins can launch their bodies out of the water in powerful arcs. Using only tail propulsion, they break through the surface with remarkable force. Their jumps are not just physical displays. They are communication, play, social bonding, and sometimes coordination within groups. But even dolphins are not the ultimate in proportional jumping ability. They are simply among the most graceful large-bodied jumpers. When we return to the smallest creatures on Earth, the pattern becomes clear. Fleas, springtails, tiny beetles. These organisms dominate when it comes to jump distance relative to body size. Because at microscopic scales, physics changes the rules. Energy storage becomes more efficient. Elastic systems outperform pure muscle, and evolution takes full advantage of that. And so we arrive at a simple but powerful conclusion. Jumping is not just movement. It is engineering. It is adaptation. It is nature solving the problem of survival through physics itself. Because in the end, the greatest jumpers are not always the biggest or strongest. They are the most efficient. And in that efficiency lies one of the most astonishing forms of movement on Earth.